Hello, my name is Viktor Morozov, and today I'd like to tell you about our work on complex event streams, processing, and forecasting. Let's begin with introducing a few definitions. First of all, let's define event as a set of features and a timestamp. It's a very wide definition, and it covers real-world events, stock market prices, behavior, customer purchases, and a lot of other events. So complex event is an event that have complex structure, and so it's described by features of different types: numeric, categorical features, binary features, and text features. Stream of complex events is a set of events ordered by timestamp. And forecasting task for such streams usually divided into subtasks. First one is forecasting probability of event happening during next time interval, and it can be considered as a classification task because target variable lies in interval from 0 to 1 and represents probability. And the second task is forecasting the amount of events, and this task could be considered as a regression task. We don't want to forecast just any event, so we'll denote events that we want to forecast as events of interest. For example, we don't want to know that some customer is gonna buy something. We want to know that this specific customer will buy some product. So the main motivation for this work is that almost all real-world events can be described by a set of features of different kinds, and we want to use all available information. So we don't want to discard any of these features because we don't know how to work with them. Also, existing approaches are mainly focused on creating specific handcrafted features, and so these features are not applicable for other tasks. And complex event stream forecasting can be applied in a wide variety of areas, such as predicting the prices in stock markets, amount of clients' purchases, traffic flows forecasting, and forecasting the number of taxi orders, and many other tasks. So now moving on to our proposed approach, it consists of two steps. First step handles the complex structure of events and performs mapping from this complex structure to dense numeric representation in some latent feature space. And the second step is about forecasting event streams using this built latent representation. First of all, let's see some properties of our initial data. Each event is described by a set of different features. Time intervals between events can be different, and aggregation over arbitrary time interval is impossible. This means we cannot use classic methods for time series forecasting, for example. Okay, first step is feature pre-processing. We are keeping all our numeric and binary features as is, and we're replacing each categorical feature with a set of corresponding binary features. And after this step, we obtain on the numeric and binary features here. So if initial data has feature city equals to Moscow for this event, now we have binary feature city Moscow equals to 1 and city, for example, Tokyo equal to 0. So after the feature preprocessing, we obtain the representation of events that is possible to aggregate over time. However, it can be excessive because of a lot of binary features in event descriptions. And now we use dimensionality reduction methods such as non-negative matrix factorization or neural autoencoders to reduce the dimensionality of feature space and also obtain a dense representation. And we will further denote the dimensionality of reduced feature space as k. And also for each event, we set the label y. And this label is equal to 1 if this event is our event of interest, and it's 0 otherwise. So now we can aggregate events. This aggregation is performed as follows. We split timeline into chunks of some size, delta t. We aggregate values of dense latent features by averaging these features. We are aggregating set of labels for each time interval according to our task. It's different for regression and classification. And we are merging text descriptions in each time interval. And extracting text features is performed as follows. We get our merge text descriptions for each time interval. Then we extract numeric features from these texts using any method you like, for example, LDA, TF-IDF, Word2Vec, LSTM embeddings, or any other. And in this work, we used LDA. This stands for latent declear allocation, and we extracted numeric features from these texts, and we simply concatenate them with numeric features from previous step. So moving on to the forecasting section, the task of forecasting is to estimate the label of the next time interval. For the classification task, this label is probability of the event, and for regression task, this label is the amount of events that will happen. To forecast this label for the next time interval, we use L previous time intervals as historical data for forecasting. In addition to the features we discussed before, we are also introducing two more numeric features: the total number of events occurred during this time interval and the number of events of interest occurred during the time interval. These two features add explicit autoregressive component, and as we will see in our experiment section, these features improve the quality of forecasting. One more thing we need to do is perform logarithmic transform of our target variable, because in the task of forecasting the amount of events, the target variable is a counter, and hence it has a skewed distribution, close to Poisson distribution. And to reduce the skewness of this distribution, we perform logarithmic transform. On the picture, we can see the results of transform. And after the transform, the original value of the counter can be restored in the following fashion. So, I described how we perform building latent representation and how we perform forecasting using this representation. One very important property of built representation is that we were able to get this interpretation for each latent topic, because it will be much easier to analyze the results and analyze the representation itself. So, for example, for a simple method NMF, we can get interpretation out of box, because when using NMF latent topics, they're just non-negative linear combinations of initial features. So we can pick some topic, for example, topic number 2, and then we analyze the weights of this linear combination. All of them are non-negative, and here on this example we can see that the greatest weights correspond to initial features of web type firearms and attack type 1 arm assault. It means that these two features have the greatest contribution in the topic number 2, and in this way we can get the interpretation of the topic based on a set of initial features. In case if we have a more complex way to build a latent representation, we might need another algorithm. For example, neural autoencoder performs nonlinear transformations of the original data, and so we cannot get interpretation of these latent topics as easy as it was for NMF. So in this work, we propose an algorithm that uses partially available text descriptions, and the algorithm allows us to get the set of keywords for each topic to describe it. So the algorithm can be defined as follows. First of all, we should select all events that have text descriptions. Then we have to gather all text descriptions, pre-process them, remove stop words, extract all keywords, and compose dictionary out of these keywords. Then for each event we add binary features, one binary feature for each word in dictionary. And this binary feature equals to 1 for some event if the corresponding keyword appears in the text description of the event, and equals 0 otherwise. After the new binary features are added, we have to calculate value Vij as follows for each binary feature and for each latent topic. When calculated, these values show how important the specific keyword from the dictionary for a specific topic. After calculating these values, we can, for each topic, select a set of keywords with lowest values v, and then we can call a set of these keywords a topic description. So using this algorithm, we obtain for each topic a set of keywords from our dictionary that will describe the latent topic. So let's move on to the experiment section. Here let me describe dataset first. For the experiments we used the global terrorism database dataset. It's very comprehensive open source database of terrorist attacks, and for each event we had a wide range of information of different types available, like numbers, categorical features, binary features, and text descriptions. So we selected events that occurred between 2002 and 2008, and we set the size of aggregation time interval equal to 3 days, and we defined our events of interest as bombing or explosion events that took place in Iraq. Let me describe models. For our forecasting task, we used random forest model, LSTM neural network, and logistic regression for forecasting the probability of event, or linear regression for forecasting the amount of events. For building the latent representation, we used two different approaches. First one is non-negative matrix factorization. It's fast, it's simple, it's linear, it's easy to interpret. And the second one is deep neural autoencoder. It's non-linear, it's more complex, but it is also more flexible. When we were using autoencoder to build latent representation, we also incorporated knowledge from anomaly detection domain and used additional feature, reconstruction error. During the experiments, we write values of hyperparameters as follows. We set the number of latent topics equal to 10 and to 50. We performed experiments with L equal to 10 and 30, which is number of time intervals used for forecasting. We use 70% of our data as a trained data set, and we used last 30% of our data as a testing data set. Our aggregation time interval was set to 3 days. And it's very important to note that we did not aim to solve specific problem to get the best results on it. The main goal was to show that the proposed general approach is applicable for forecasting event streams. So further in the results, we will denote using auxiliary features as +A, reconstruction error for autoencoder as +R, and using both of them as +A+R or +AR. So for example, label AE10 +AR means that we used autoencoder to build latent representation, and we set the K, the number of latent topics, to 10, and we used both auxiliary features and reconstruction error. So let's move on to the results. So here is the results of classification task using our models. The metric is ROC-AU, it's area under ROC curve. The larger score means better performance. So here we can see that LSTM works better than other models, and the best way to build latent space is non-negative matrix factorization with 50 latent topics and with using auxiliary features. And as we can see, using auxiliary features helps a lot in almost any way to build latent representation. So we also decided to compare the results without using text and with using text. So in the next table we will see results of classification using text, and here we can see that the leading way to build latent representation changed to autoencoder plus auxiliary features plus reconstruction error, and here the LSTM model is also the best performing model and the score a bit higher than without using text. Okay, moving on to the results of regression task. And here the metric is MISE, it's mean absolute scaled error, and it's the lower the better. So it's actually the mean absolute error scaled on the volatility of the time series we are forecasting. And here we can see that best performing model is a random forest regressor, and the best way to build a latent representation is autoencoder, 50 latent topics, auxiliary features, and reconstruction error. And as we can see in the regression task, using the auxiliary features also increases the quality of the model. So again, let's compare this result with the result with using text. And here we can see the model is worse. This means that using the text features in the way we use them with LDA might not improve the quality on any task as it did on a classification task. And here are a few more results with using logarithmic transform in regression task. And here we can see that random forest is still leading model, but the score is much better than without using logarithmic transform. So the usage of logarithmic transform increases the quality of forecasts. And here again result with using text, which is also a bit worse than the previous one. So we can see that the using the text in the way that we use it here is not increasing the score. And here we can see an example of performance of both models. Here is a classification model, and here we can see predicted probability of event. We can see that since the prior distribution of target is not balanced, we might want to use a threshold like 0.8 or 0.85 in this classification task. And we can see here regression task results. So this is quite accurate forecast. In conclusion, I'd like to say that we propose the general approach for a complex event stream forecasting. This approach handles complex structure of events by building latent representation for these events and then using this built representation to perform forecasting. Additionally, we proposed a method to extract keywords for latent topics using partially available text descriptions for events. This method allows us to get interpretation of built latent space, even if it's a complex one. And as a future research direction, we believe that joint training of autoencoder for building latent representation and LSTM for forecasting can improve the performance of this approach by enforcing autoencoder to extract latent features in a way that they're useful for further forecasting. And thank you, I'll be happy to answer your questions.